much as I have explained, the basic idea is to break up the signal into sines and cosines, but one has to exercise some caution when it comes to the mathematics depending on the nature of the signal. That is all you have to remember. The basic ideas remains the same whether you look at continuous time or discrete time signals or periodic and aperiodic signals. In fact, today very soon we will move on to the discrete time world, where there is going to be definitely an additional source of confusion and complication, but the underlying principle is the same. It is just that the mathematics is slightly different, and maybe some practice will help you get over this confusion. So, let us get started from where we left off yesterday. So, we started to look at Fourier transform, and this Fourier transform was introduced in the context of continuous time aperiodic signals with finite energy. Now, why are we looking at finite energy signals? Basically, if you look at this equation here for the Fourier transform, you can see and we have discussed this earlier as well, the Fourier transform itself exists first of all when the signal is absolutely convergent. We have talked about this before, but in the context of discrete time signals. So, here we are extending the same to the continuous time signals. Of course, the integration runs from minus infinity to infinity. This is a necessary and sufficient condition. A slightly weaker condition for the existence of Fourier transform is that the signal has finite energy. So, this is a weaker requirement, whereas the one on the top is a stricter requirement, all right. And in any case, if this is satisfied, definitely the signal has finite energy, but not vice versa. And as long as this is satisfied, you can say that the Fourier series that we had here, the Fourier integral that we have here converges in a mean square error sense. What we mean by mean square is as we include more and more frequencies, the error between the approximation of x of t. Remember, we talked about this approximation yesterday. One can construct an approximation of a signal using Fourier transform by only concentrating on a select set of frequencies, and that is the basic idea that is used whenever you want to approximate a signal using Fourier transform. So, here as well, instead of including all the frequencies in this integral that you see in the synthesis equation, I can focus on a band of frequencies, and as I include more and more frequencies, the error in the approximation starts to decrease, and the weaker condition says that as long as the signal has finite energy, the error will go, the squared integral squared error will go to 0 as f goes to infinity, that is as you include more and more frequencies. Whereas the first one is a strict one, it says basically as long as the signal is absolutely convergent, this integral will get you the signal of interest. Anyway, so those are existence conditions. What you have to remember practically is Fourier transform of any signal, and here I also want to broaden your horizon. Although we are talking of signals, you should think of these as sequences as well, because very soon we shall talk of Fourier transforms of autocovariance functions, and the autocovariance function is not a signal per se, but it is a sequence. So, whatever you are learning for signals equally applies to sequences, it is just a different terminology. So, here we are looking at continuous time sequences, and what we are doing is we are saying I have a continuous time aperiodic finite energy signal, and I am going to look at the frequency content of the signal. Here we are not looking at fundamentals and harmonics, we just want to know what frequencies are present when you think of the deterministic signal. But a better question to ask is what frequencies are contributing to the overall energy of the signal. Now, why I say that this is a better question to ask is when we move to the world of random signals, we do not think of necessarily, although it is possible to do that, necessarily we do not think of signal reconstruction. we do not think of necessarily signal decomposition. We are mostly focused on energy or power decomposition, because we are going to talk of random signals and they are power signals. We are going to talk about power decomposition rather than signal decomposition, and that is why I have been emphasizing this transition from signal decomposition to power or energy decomposition. Sorry. Sorry. So, here let me now go further and show you the energy decomposition. All of this we have discussed, I am going to move on. This again is due to a Parseval's relation, which shows that energy is conserved in both domains. But apart from that statement, what this tells us is how the frequencies in a certain band are contributing towards the overall energy, right. If you compare this with what you saw for periodic signals, we had first of all power decomposition earlier, and secondly, while the signal still had in the time domain we had the integral, in the frequency domain we had a summation, because we were only talking of fundamentals and harmonics, whereas now we have a continuum of frequencies, and that is why we have now an integral in the for the frequency domain as well. Now, earlier we talked about line spectrum. What I mean by earlier is, for periodic signals we talked about line spectrum, simply because when we plot the square of the Fourier coefficients versus the index, it is only defined at some at discrete values of n and so on, right. This is a typical sketch of mod C n square versus n. We call this as a line spectrum, and we said we cannot think of a density here, whereas now with the aperiodic signals, since we have a band of frequencies or a continuum of frequencies, we can think of a density function. What we mean by density is energy density here, because we are focused on energy signals, and this relation due to Parseval tells us or gives us a hint of what could be an energy density in frequency. Earlier we had defined an energy density in time, and the energy density in time was defined as simply mod x of t square. Why did we define this as energy density? What was the reason for defining this as energy density? Yeah, the area under this will give me the energy, right. Now, we have a hint here. What would be the energy density in frequency? So, if I were to ask what is energy density in frequency, that is energy per frequency, that would be mod x of f square, that is it. So, magnitude square of the Fourier transform is energy density. So, there is a striking similarity in the expressions, but you have to remember after all that the area under this energy density should give me the energy. Area, of course, the frequency is running from minus infinity to infinity. Now, if I want to know what is the energy contribution, or you can say the energy contained in a band of frequencies, then you can do that. You can actually get the energy over a frequency band f1, f2 by simply integrating the energy density over that band naturally. And whenever you have difficulty understanding these densities, go back to probability density functions. The role of the probability density is to allow me to calculate probabilities. Here they are allowing me to calculate energies, that is all, or power, whatever. Soon we will talk of power spectral density also. So, wherever you look at densities, the concepts remain the same. The area under the density will give me some quantity for which it is a density function, and then you can think of moments and so on. In this course, we do not per se deal with moments of these densities. We are only talking about density functions, that is all. In a more advanced course, we go into the moments of this density and see how they are useful in signal analysis. As I said, in a joint time frequency analysis, we look at the moments, namely duration, bandwidth and so on, or the mean time, mean frequency, center frequency and so on, which will give us some valuable insights into the features of the signal. Okay. So, any questions on this? as I said, now you can see a pattern, whether it is continuous time periodic or aperiodic, we come up with a synthesis equation, then we have an analysis equation, then we briefly talk about its existence and then move on to either power or energy decomposition. If a density function can be defined, we define so, otherwise not. But the utility of this analysis is what you have to understand. While the utilities are manifold, what we are focused on is the decomposition of the energy or the power, right. Once again, a plot of mod of x of f square versus frequency. Here once again we only plot over the non-negative frequencies because it is symmetric, you can show it symmetric with respect to frequencies, tells us what are the predominant frequencies present in the signal, right. For example, mod x of f square can look like this, flat. What does it tell us? All frequencies are contributing uniformly to the overall energy. What kind of signals would have that? Impulse, right. An impulse signal, Dirac, in fact it is continuous time function that we are looking at, therefore it is a Dirac that you have to think of. And let me tell you, you can't straight away use this integral that you have used earlier to evaluate the, for example, you can't use the synthesis equation to come up with the Fourier transform of a Dirac. You need what is known as theory of generalized functions, do not get scared, we will not talk about it. But for special class of functions which for which you cannot just ordinarily evaluate this integral, there exists a theory of generalized functions that will allow you to compute the Fourier transform. In any case, so this is a very important thing to remember, the Fourier transform of an impulse, whether it is continuous time or discrete time, has a flat energy spectral density, all right. And there are many other possibilities, it could have like you could have a density function like that looks like this or maybe this one. So, there are numerous types of density functions that you can have depending on the frequency content of the signal, what makes up the signal. And remember, ultimately there is no signal without a system. So, very soon we will talk about if this is some density of some function, some signal x2 here, we may talk about this in the discrete domain, but does not matter, the results are the same. So, you can think of if this is the density function of some signal x2 and imagine that to be generated by g which is being driven by an input x1, then you can use these densities to draw inferences about what characteristics the system has, provided you know the frequency content of x1, and that is what leads us to the filtering nature ideas. Okay. So, let us move on and now look at an example. We have talked about all of this. So, here it is a finite duration rectangular pulse signal. Unlike in the periodic case where I gave you expression for one period, this is exactly exists only for the period that I have shown, for the interval that I have shown, because we are looking at finite duration signals, periodic signals. Okay, so, the Fourier transform in fact given by the sinc function. Sinc function is your sin c function that you must have encountered in different situations, and this integral is very easy to evaluate, there is nothing to be scared about. How does a sin c function look like? It looks like this crazy creature that you see in Hollywood, some alien movies and so on, which has its hands spread all over, as I say, कानून के हाथ लंबे होते, something like that. So, that is what you see here. If you look at the shape, on the left hand side we have the energy density in time. It is not the signal, remember the signal also looks similar. What we are showing is mod x of t square, and on the right hand side you have mod x of f square. This is not the Fourier transform or the magnitude of the Fourier transform, all right. Now, what do you notice here? The finite duration signal that we had has an energy spread over a finite interval in time. That is, the energy goes to 0 after some finite time. Let me say energy density goes to 0, let me not say energy exactly. Whereas, when you look at energy spectral density, that is mod x of f square, it does not go to 0 identically even after after any finite frequency, it only goes to 0 asymptotically. Now, this has profound implications in time frequency analysis, that is when you want to know, for example, what frequencies were present at what time. We will talk about this now, duration bandwidth product being bounded below by some quantity. What this result says is, in fact I will show you a couple of examples as well, is that whenever I have a signal whose energies are localized over a finite interval in time, you cannot have the energy also localized over a finite frequency band. Any signal whose energy is localized over an interval in time will have an infinite spread of energy density in frequency as well, in frequency. So, the vice versa applies. If I have an energy spectral density that is only concentrated over a band and not like the one that you see here, then you are guaranteed that the energy density in time will be spread all over. We just now saw, right. So, this is what we have drawn here as a flat line is an extreme case of the example that we are looking at. The Dirac is extremely localized, you can't have a more localized than a Dirac. Okay, so let us look at an example to understand this relation between so called duration, which is a measure of the spread of energy density in time, and bandwidth, which is a measure of the energy spread in frequencies. Bandwidth is a term that you would encounter in almost every field of signal analysis, in control, in signal processing and so on. And typically we talk, even in modems, when we talk of modems, we talk of bandwidth and so on. So, bandwidth has got to do here with the spread of energy in frequency or energy density in frequency. So, let us look at an example here, another example where I have a finite duration sinusoid, not like your regular sine wave. Of course, I have taken a complex exponential, and it turns out that the Fourier transform is once again a sine C function shifted in frequency. So, here is how the signal looks like in time. It is a finite duration sine wave. You see both the real and imaginary parts, that is what I am showing you here, because it is a complex sine wave. And what you see on the right now, on the top you see the energy density of the signal in time, and what you see at the bottom is the energy density of the signal in frequency. Okay. So, you can see that the energy density exists only over a finite interval in time, whereas the energy density is spread all over in frequency. Now, suppose I increase the width of the signal, what should happen to the energy density in time? It will spread. Then one should expect a shrinkage in the energy spread or the bandwidth of the signal. So, let us see if that happens. So, here I have now extended the duration of this sinusoid, complex sine wave, and as expected, the energy density in time has dilated, has increased. But what do you see for the energy density, spectral density? It has shrunk, right, you can compare. So, here you have a larger bandwidth, meaning more and more frequencies are coming in to explain the signal, and as I expand the signal, fewer and fewer frequencies are contributing, and that has got to do with the very nature of the Fourier atoms itself. We will not go deeper into why this is happening, but the intuitive answer to that is it is just the nature of the basis functions, or sorry, building blocks that we are using. Where in a continuous time Fourier transform case, strictly speaking, we cannot use the term basis functions, we can only use atoms, whereas in the periodic case we can. Anyway, so what you see here is that longer duration results in narrower frequency spread, and this is just a general information for your result. This is a fundamental result in time and frequency analysis, which is also known as the uncertainty principle for signal analysis. Although there is nothing uncertainty here, there is no randomness or probability here. The only reason why this is known as uncertainty principle relation in signal analysis is because of its striking similarity with some other result that you see in physics. What is that? The Heisenberg's uncertainty principle, right, which says that you cannot really locate the position and the velocity, you can't really locate the position and measure the position and velocity of a particle with arbitrary accuracy at the same time. If you have located a position, then you have lost, you have huge uncertainty about its velocity and vice versa. So, the sigma square t that you see here, although it is not corresponding to any random event, it still corresponds to a second moment. The sigma square t is a second central moment of the energy density in time, and the physical meaning of that is the duration. It gives you an idea of how long the signal exists in time. It is not exactly equal to the duration of the signal, but it is a measure of that. Pretty much like your variance, your variability gives you an idea of the spread of outcomes. And sigma square omega is the bandwidth. It is once again a measure of the spread of energy in frequency. So, what it says is the energy spreads in time and frequency cannot be arbitrarily small. If one shrinks, the other has to expand and vice versa. Okay. What is the implication? Again, we are not going to talk about the implications. We may not even be hampered by this result in this course, but in a broad scheme of things, we are limited by this result in any joint time frequency analysis. When I say joint, I would like to know, for example, over what duration what frequencies existed or contributed. When I am doing that, see, you think of time domain analysis as looking at this direction and frequency domain analysis as this direction. They are kind of orthogonal, you can think of, and joint time frequency analysis is looking at some diagonal trying to figure out what is happening here and there, and it says you are limited when the moment you do a joint time frequency analysis. Anyway, so we will move on, and before we move on to the discrete time world, I want to introduce what is known as this Fourier stieltjes transform. It is not a new transform, let me tell you, do not get scared. Remember, you have two different expressions in the continuous time case, where depending on whether it is periodic or aperiodic. In the case of periodic, we do not use the term Fourier transform, we just say the Fourier coefficients, and then we have an expression for the Fourier coefficients that we saw in yesterday's class. And today we talked about Fourier transform, which is an integral. So, on one hand you have summation and the other hand you have integral. Is it possible to fuse both these expressions? And that is what Fourier stieltjes transform does. It says define an increment dx of f as x of f times df. So, you have this equation that you saw for Fourier transform, right, integral x of t e to the minus j 2 pi f t dt, and go back to the synthesis equation. So, you have this x of f e to the j 2 pi f t df. Replace this x of f df with some increment of, think of it as an increment in x of f, that is what it says. So, when you do that, you get this expression. All we are doing is we are rewriting the synthesis equation using this dx of f, that is all we are doing. Now, what is the advantage of this? How does it help me fuse both these results? It helps me in fusing these results by saying that whenever the signal is periodic, for example, then I let dx of f to be this, that is it looks like spikes. So, the dx of f would only have Cn's, right. This is how dx of f would be. It is not defined at intermediate frequencies at all, it is only defined at discrete set of frequencies, so that the integral boils down to summation. When it comes to aperiodic signals, I am going to let dx of f being defined as x of f times df. Then I get the Fourier synthesis equation. So, that is the basic idea. You see that, and this is a standard trick that is used also in probability density functions and random variables and so on. Although I did not discuss that, you can write the expression for the probabilities for both discrete valued and continuous valued case by adopting this kind of a strategy. In the continuous valued random variable case, we say the probability is simply the integral f of x dx, right, whereas when it comes to discrete valued case we do not use that integral, we simply use the mass functions and say it is sigma f of x. You can fuse both those expressions using the same trick, or we have not discussed that, but you can now think of the same way. So, this is useful in fusing both words, but otherwise nothing much more. We will make use of this expression a bit later on when it comes to random signals. Okay, so let us move on now to the world of discrete time signals, unless you have any questions.